So the focal length of 1 is less than the focal length of 2, or the focal length of 2 is greater than the focal length of 1. And if the focal length of 1 is less than the focal length of 2, then the power, the refracting power, or the power of this lens with a shorter focal length is greater than the power of this lens with a longer focal length. The reason is that power of a lens is given by 1 over its focal length. And you know that in fraction, when you have a fraction and then the denominator is less than another one, the whole value is greater. So because P1 will be equal to 1 over F1. Then P2 will be equal to 1 over F2. But because this denominator, hello?
Please, I can't see.
I think the problem is where the reflection is. Let me bring it down. So because the power of a lens is given by 1 over the focal length in focal length in meter. Okay, it means that if we look at the power of the lens 1, P1 will be equal to 1 over F1, and P2 will be equal to 1 over F2. Okay, by infraction, whenever the denominator is less, the whole result is greater. So this is greater or larger. Let me put it that way, larger in terms of power, and this is less. So what we can deduce from here is that if a lens has a shorter focal length, then it means it can deviate the path of light better. Okay, so the SI unit of the power of a lens is per meter or diopter. Okay.
Mr.
Hello.
Please, can you explain why P1 is larger than P2 again?
I said, you see, when you look at the drawings over here, this is from the optical center to the principal focus. This is the principal focus. Okay, this distance is less than this distance. So F1 is less than F2, or F2 is greater than F1. But the power of a lens is given by 1 over 8 focal length. So if I'm calculating this power, then it means this is 1 over F1, and then P2 is equal to 1 over F2. F1 is less than F2, and because the denominator is less, the whole fraction or outcome will be greater than the other one. Okay, all that I'm saying is that if you have, assuming F1 is equal to 5 centimeter and F2 is equal to 10 centimeter, then P1 will be equal to 1 over, but here when you are expressing it, you have to change this to centimeter before, because that's the SI unit, or before you can call it as maybe diopter. So this is 0.05 meter, right? Divided by 100. Then P2 would be equal to 1 over 0.1. If you divide 1 over 0.05, point it, let's see what that will give you.
20.
So 100 on 5. This is 20 diopter. Okay. Then this is what?
10.
10 diopter. Okay. So lenses with a shorter focal length okay, are powerful, meaning that they can deviate the path of light better than those lenses with a longer focal length. So the lenses used in the microscopes, they have a very short focal length. This one, for instance, has a very short focal length. This one, I think, has a focal length of 5 centimeters. Okay, so if a lens has a shorter focal length, then its ability to deviate the path of light is higher than those ones with a longer focal length. Are you okay? Are you fine?
Yes, please.
All right. If there's no question, let's move on. If you have a question, ask. Rome, are you here?
Yes, please.
Oh, okay. All right. Then let's move on to
Adria,
hello.
please, the D by the 20, what's that?
Diopter. This unit diopter is
Adria, please,
represented
where?
as capital D. This unit, that's the unit of power of a lens or mirror. Okay, so diopter is shortened as capital D. So that's what I've written here. And it's a positive. It's a positive because this lens converges light. All right.
Studio.
Hello, Nana.
Please, I'm still copying.
Pardon? Kezia.
Please, yes, please.
Okay,
Please, I'm copying the other side. Thank you.
Okay, hurry up. So the next thing we have to look at methods of determining the focal length of a lens.
Mr.
Hello.
Mr. Dia, please, are you saying that the shorter the focal length, the greater the power?
Exactly. That's what I'm saying.
Yes, please. And Mr. Dia, please, the diopter, is it the unit for the power?
Exactly. But
Yes.
it is the unit of power when the focal length is expressed in centimeter. Okay, meaning that if the focal length is not in centimeter, you cannot write the power as diopter. No. So before you can find the power quickly, if the unit of the focal length is in centimeter, convert it to meter before. All right.
Yes, Hey, please. dear.
Hello.
Please, you said if is the when is what is it called? When the focal length is given in
Centimeter.
centimeter.
Yes.
So
And
what
you are
if it's
looking.
given in millimeter? You are not supposed to convert.
Oh, you have to convert. You have to convert. We are always converting to SI units. Okay,
What?
so it is either you express the unit as per meter or diopter. You can't express it in diopter when the unit is in centimeter. No, that's an offense. Determining the focal length of a lens. And this is very important to look at because we'll be using it in light experiments. We have 3 methods we often use in our light experiment. One, the method of approximation. Method of approximation. 2, method of displacement. Okay, varying varying object distance to determine image distance. And then the other third one we often use is the method of displacement. The method of displacement. The method of approximation is the quickest or the fastest way of determining the focal length of a lens. So most often in WASI, if they just want you to roughly determine the focal length of a lens, that is what they ask. That cannot be exact, but it will be close. That's why we say approximate method of determining the focal length. You approximate it. They will always give you something close. So if we are going by the method of approximation, how do we do it? Approximate method. In the approximate method, we have a lens. We have a lens, a distance object, maybe a tree somewhere, or in the lab, we often have louvers. Okay, maybe a tree. Then we have the lens placed on the lens holder. And then a screen placed behind it. The screen captures the image of the distance object. So this is the lens, convex for that matter, and then this is the screen. So by the approximate method, all that I'm doing is that I have this lens and I have to be moving it. Let me demonstrate it with the lens I have. So if this is the lens, I'm presuming that the screen is behind it. All that I do is that I'm capturing the image of a distance object on the screen. So I have to move it, move the lens, so I get a very sharp or clear image of the distance object on the screen. Okay, so the lens is kept, it's moved. It's moved. As I move it, all that I'm doing is that I want to capture the image of this distance object. Here, I'm using a tree, or it can be the louvers in the lab, the louvers around any distance object. So I move it, I'm adjusting it. So I get a very sharp image of the distance object on the screen. Real image. Once it is captured on the screen, it's a real image. So where I'm so convinced that, oh, this image of this thing that I see is so sharp, then I cease to move the lens. Okay, so if I'm assuming this position of the lens is what gave me the sharp image. Now this distance between the lens and then the screen would always give you the focal length of the lens. So as I move it back and forth, when I manage to get the sharp image of the distance object on the screen, Then I measure the distance from the screen to the distance from the lens to the screen. Then by approximate method, I have the focal length. So it is always the quickest and then the fastest way of determining the focal length of a lens by adjusting the lens position to get or to have a very sharp or clearer image of a distance object on a screen. And when you have that clearest image, the distance between the lens and then the screen is equal to the focal length of the lens. Please, are we okay?
Yes, please.
Please, can you go over one more time?
Okay. So all that I'm saying is that by the approximate method, you direct the lens to a distance object, an object that is very far. Okay, I'll demonstrate this for you when you come to school. So, okay, so the image of a distance object, it can be a tree or in a lab. Okay, we often even use the louvers around, and then the trees around are also used. So you have the lens, you have the screen, and what you do is that you adjust the position of the screen. Okay, so a point where you have a very sharp image of the distance object on the screen. Okay, so if you manage to get a very where you are convinced to be, oh, this image that I see is so sharp. Okay, then when the image is sharp, then the distance between the screen and then the lens is equal to the focal length of this lens. I tried with this lens. I tried with this, and that is how come I realized that the focal length of this is around 5 centimeters. Okay, so when I moved it and I measured the distance between the image I saw to be so sharp and then the lens, I had 5 centimeters, giving me the focal length of the lens. Okay, I know this is something you can easily master, so you relax. Let's go through the theory. Then the other method is varying the object distance to determine the image. Here, there is a source of light, which in our case, we use what we call illuminated objects. An illuminated object is an object that produces light. So we have a box. A box, one end of it has a hole. Then a bulb, this incandescent bulb is put in a box and then lighted through electrical means. And this is what we call as the illuminated object. I don't know if you've seen, any of you have seen that in the lab before. We call it ray box.
Yes.
Yes, that box with the ray box. And that is what we are calling as the illuminated objects.
Mr. Edia, please, the light is reflecting on the thing you are drawing, so I can't really see.
Okay. Let me bring it down. Now I have a big board, so Mishra, don't worry. I have a big board, many markers, but few are properly working. So this is a hole with wire, okay? Then we have a bulb. I'm here drawing, okay, bulb, something to represent bulb. Okay, in a holder. This is connected to a source of light. It's actually connected to a source of light. So this is what I'm saying to be the illuminated object, an object which produces light. Okay. And this is what we call as a ray box. Then we have
Mr. Dear.
hello.
Please, I can't see.
You can see. You mean you can see?
Please, the light is reflecting on the board.
Oh, here too. I'll take a shot. So I'll take a shot, okay?
Mr. Dear,
Hello.
please. You said something was connected to a source of light.
Yes. You see, the bulb is powered through electrical means. So this is there's a wire connecting it to, okay, the source of light. That's what I was saying. Okay.
Thank you.
So this is a lens holder. Okay, there's a lens on it. What you see as the door is the lens holder. It holds the lens because the lens would have to be in position, okay, to receive light, okay, to receive light from the illuminated objects. So this is the lens placed on the lens holder. Now light from the source incidents and is captured on a screen. This is a screen. Okay. Okay. Now, from the lens to the object, the illuminated object is the object. This is what we are calling as the object distance. U. Then from the lens to the image of course will be captured on the screen. So this is V. Please, are we okay? Now what we do is that you are given different positions of the objects. Okay, object distance, maybe in a certain increasing or decreasing order. Okay, maybe 10, 20, 30, 40 to 50. So initially what I do is that I'm from here to here, from the illuminated objects to where the lens is, I measure 10 centimeters. Then I keep this distance fixed and then move the screen back and forth till I get a very sharp image of the objects on the screen. Okay, so I hold the screen, move it back and forth. So I'm able to capture a very sharp image of the object on the screen. Then I record whatever I had as the image distance. Okay, then I come and then measure the second 20 centimeters. Okay, then this time around, let U be equal to 20. You take measurement, practical, that's what you do. You measure, after measurements, you move this back and forth. So you are able to get a very sharp image of this on the screen. Then you record the distance from the lens to the screen because the image is on the screen as V. You also record it against the 20. So every U gives you a corresponding V. Please, are we okay? Are we okay?
Mr. Dear, please, I'm still not clear
On what?
like the explanation.
What I'm saying is that okay, you measure the object distance as what has been given to you from 20, 10, 20, 30. So initially, all that I will do is that I have to make sure the distance between the illuminated object and the screen is 10 centimeter. So the next thing I have to do is to move the screen. You keep this fixed. The lens position is kept fixed over here. Then you move the screen back and forth so you get a very sharp image of this, okay, illuminated object on the screen. Where you think the image is sharp, then you measure the distance from here to the sharp image, and that will be V. So this V, you record it against 10 because it is the 10 centimeter which gave you that. Then you pick the second object distance, 20. You measure from the illuminated object. This time you adjust the lens and then to have 20 centimeter. Then you come and then pick the screen, move it back and forth till you get a very sharp image of this object on the screen. Then you record it against 20, 30, 40, 50. So every object distance gives you a corresponding image distance. Please, are you okay, Gloria?
So, Mr. Ria, does it mean with this method you only move the screen?
Exactly. You take your object distance measurements, adjust the screen till you capture a very sharp image of this object on it. Then you come and then measure for V, the image distance.
So it means the object distance should be fixed.
The object distance, okay, for each measurement must be fixed.
Okay.
So if I measure 20 from the illuminated object to the screen, to the lens, all that I do is to move the screen so I get a very sharp image on it. Then I measure from here to here. Is that okay?
Yes, please.
Please, if you have any question, ask before we continue.
Mr. Ria,
Deborah.
please, in this case, is the object the light?
Yes. The object is the light, but it's in a box. So you have to measure the end of the box. That's why I started here to the center of the lens holder. We'll do this in school so you understand where to take your measurement and end. Is that okay?
Yes,
Nana
please.
Dubia and Co, are you okay?
Mr. Ria, please, you said you capture it too.
Okay. Let me take a shot and then send it to you. Send it to the platform. Okay. Let me take the shots to the platform. Then. Hello.
Just came to, I'm here, but I don't understand.
Who?
It's Priscilla because of the network.
I'll send you the video.
Okay.
It isn't difficult, but I think it's better you go through the theory and then, okay, when you do it, you realize, oh, is that what it is?
Mr. Kia,
Hello.
is the object distance is from the very edge of the illuminated box to the middle,
To the middle of the lens holder.
and it's always 10 centimeters.
Oh, I'm giving an instance situation. Assuming, okay, our variation is such that we start from 10, 20, 30. Okay. So you measure based on what you see, the illuminated object is like something like this. Within this, we have the box, the light put within. Then a hole is created so that when we plug the light on, ray of light would permeate through this. Okay, so the illuminated object is actually like this. So if you are taking measurements, the illuminated object, the edge of it, okay, to the center of the lens holder is what will give you the object distance. Okay. So for every measurement, U is fixed. All that you do is that you have to move the screen back and forth till you get a very sharp image of this on the screen. It will be captured on the screen, real objects. Then you measure from the center to the screen to get your U, to get your V. Then you come to 20, measure 20. Do the same thing, get a value for V, record. You come to 30, on and on till the last U value. Is that okay?
Yes, please.
Then when you finish within the table, you see, because we have 1 on F, the length formula, 1 on F is equal to 1 on U plus 1 on V. You find, let me clear parts of this and then extend the table. So on the table, I have 1 on U. Because of this formula, I have to also find 1 on V. So after getting value for U is given, after getting values for V, you find 1 on U, and 1 on U is certainly 0.1. Okay, 1 on 20, which is
0.2.
0. Is it 0.2?
Yes, please.
Okay, then 1 on 30, 1 on 40. Don't forget, each U value gave you a corresponding V. So you find 1 on V2, 1 on blah, 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 blah for each V value. So you have to get this in your table. Please, you don't forget the units. Centimeter, this is slash centimeter, this become per centimeter, this is also per slash per centimeter. Okay, so this is what you have in your table. Let me see, I think we have less than 1 minute to break for the 8 minutes. Can I clean this side?
Yes, please.
I'm already cleaning them. When you finish, okay, getting values for UV, you plot a graph of 1 over V against 1 over U. Don't forget, in our graph works, the vertical is always the word dependent variable. And then the independent variable is at the x-axis. So you plot a graph of, oh, my marker. Graph of 1 on V against 1 on U. Is that okay? So